Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Photoluminescence, that is PL, under the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the principle of photoluminescence, that is PL, will be described. Secondly, in this module, the different modes of photoluminescence will be studied. Third, the basic instrumentation of photoluminescence is described. Fourth, the relation between absorption and emission spectrum is studied. Finally, the applications of photoluminescence along with the limitations are discussed. Let us study what is photoluminescence. Photoluminescence is basically an interaction of light with matter. Photoluminescence spectroscopy works in a non-contact mode. It is non-destructive technique of examining the material's electronic structure. Let us study the basic principle of photoluminescence. When light strikes a sample, it gets absorbed by imparting its excess energy to the material by the phenomena known as photoexcitation. This photoexcitation process is shown in figure. One manner method in which sample dissipates this excess energy is through light emission, that is luminescence. In case of photoexcitation, luminescence is known as photoluminescence. Excitation causes material's electrons to occupy the allowed excited states. These excited electrons return to the stable, that is equilibrium or ground state, by dissipating the extra energy in the form of either light, which is known as radiative process, or by any non-radiative process. The emitted light energy, which is photoluminescence, is linked with the energy difference in energy of the two electronic states taking part in the transition between excited and equilibrium states, whereas the portion of radiative process decides the quantity of light emitted. Let us discuss the significance of photoluminescence. In photoluminescence systems, the aggregation of chromophore commonly causes quenching of light emission. Due to aggregation caused quenching, which is also known as ACQ. This implies that it is essential to utilize and study fluorophores in diluted conditions or as isolated molecules. This causes poor sensitivity of devices using fluorescence such as biosensors and bioassays. In light emitting process, some examples have been described in the recent times about luminogen aggregation, where it has played a constructive role instead of the destructive role. With respect to the solid state device, a process known as aggregation induced emission, which is AIE, is of huge potential importance. Fluorophore luminescent properties can be examined by the technique known as photoluminescence spectroscopy. Let us study the different modes of photoluminescence. First one is the resonant radiation. In this process, a specific wavelength photon gets absorbed with the immediate emission of equivalent photon. This process does not involve any appreciable internal energy transitions between absorption and emission. Further, the time scales of the process is of the order of 10 nanoseconds. We next discuss the fluorescence, the chemical substrate when it is undergoing the internal energy transition by emitting photon before returning to its ground state. Certain joule of absorbed energy gets liberated, such that the emitted light has lower energy in comparison to the absorbed one. Fluorescence is one of the known mechanisms whose lifetime is very short, of the order of about 10 raised to the power minus 8 to 10 raised to the power minus 4 seconds. Next, we discuss the phosphorescence. It is a radiation based transition wherein the absorbed energy experiences electronic transitions having different spin states. That is inter-system crossing, which is ISC. Phosphorescence phenomena lifespan is typically from 10 raised to the power minus 4 to 10 raised to the power minus 2 seconds, which is considerably lengthier in comparison to fluorescence lifespan. Thus, phosphorescence phenomena occur rarely when compared to fluorescence, as the molecule in its triplet state has a more chance of experiencing inter-system crossing to lower energy state before the occurrence of phosphorescence. We will now describe the relation between absorption and emission spectrum. Figure 2 shows the energy level diagrams, which mentions that Y structure is seen in the absorption as well as emission spectrum. Also, Y the spectra are roughly mirror images of each other. We can see at lower energy the chance of fluorescence and phosphorescence is more than absorption, which is the energy of excitation. In case of absorption, lambda naught wavelength means transition from the ground state of vibration, that is S naught to S1. When absorbing radiation, S1 molecule, which was excited vibrationally, goes to lower vibrational level before emitting any radiation. The lambda naught wavelength corresponds to transition of very high energy. The cascade of peaks occur at higher wavelength. Both emission as well as absorption spectrum are likely to have mirror image relation if the spacing of vibrational levels are approximately equivalent and if the probability of transition are alike. In figure 3, where the emission as well as excitation spectra of anthracene, which possesses the identical mirror appearance relation at the absorption and emission spectra are shown. We can see lambda naught transitions do not overlap completely. As depicted in figure 2, a radiation absorbing molecule, which is primarily in its ground state, is not have a firm geometry in addition to solvation. The transitions in the electronic states are rapid in comparison to atoms' vibrational movement or the solvent molecule's translational movement once the radiation is absorbed. This S1 excited molecule yet have its geometry as well as solvation is not strict. Geometry in addition to solvation is modified to an utmost appropriate amount soon after the excitation. This rearrangement lowers the energy of excited molecule. When an S1 molecule fluoresces, it returns back to the S0 state having S1 geometry and solvation. This unbalanced arrangement must have a higher energy than that of an S0 molecule having S0 geometry and solvation. The net outcome has been shown in figure 2, in which the excitation energy is higher than the emission energy. Let us study the instrumentation of photoluminescence. The fluorescence from a sample is recorded and measured by an analytical device known as spectrophotometer. Scanning of the excitation, emission, or both wavelengths is done in order to record the fluorescence. Through extra attachments, study of signal deviation with respect to time, temperature, concentration, polarization, or other variables is observed. The block diagram of fluorescence spectrometer is represented in figure 4. We can see that the fluorescence spectrometers use laser sources which has the excitation monochromator, which is a wavelength selector, then sample cell followed by slits onto the emission monochromator, then the detectors connected to amplifier and recorder for detecting and recording the corrected spectrum. Let us now discuss about the source of illumination. The source of light which is used is a continuous type, that is 150-watt ozone-free xenon arc lamp. Lamp's light is accumulated by a diamond turned elliptical shaped mirror, which is then focused onto the excitation monochromator's entrance slit. A quartz-based window is used to isolate excitation monochromator from the housing of lamp, which vents heats out of the device and shields against the unlikely occurrence of failure of lamp. Resolution over the complete spectrum stretches and reduces spherical aberrations and redifraction. Let us study about monochromators. There are two types of monochromators, that is excitation and emission monochromators. Entire reflective optics is used by it in order to keep great resolution over the full range of spectrum as well as to reduce aberrations, spherical and read diffraction. Now we'll discuss about gratings. Reflection grating is a crucial part of a monochromator whose purpose is to disperse striking or incident light through grooves which are positioned vertically. Spectra are acquired by gratings rotation, which contain 1200 grooves per mm and are placed at 330 nanometer excitation at 500 nanometer emission. To overcome oxidation of the grating, it is coated with a protective layer of MgF2. Next, we discuss about slits. Very flexible slits are used at the entrance and exit points of the monochromator. Bandpass of the incident light is determined by the slit's width on the excitation monochromator, whereas fluorescence intensity signal is controlled or recorded by signal detector by the emission monochromator slits. When setting slit width, the trade-off is intensity of signal versus the spectral resolution. In a case where slit width is wider, it shows decrease in resolution because extra light falls on the sample as well as on the detector, whereas when narrower slits are used, higher resolution is obtained but at the cost of signal. Next is shutter. Beneath the excitation monochromatous exit slit, an excitation shutter is placed, and its purpose is to shield the sample from photo-bleaching or photo-degradation by long exposure to the light. The detector is protected from the bright light through an emission shutter, which is positioned just prior to the entrance of the emission monochromator. The sample compartment. In the sample compartment, several optional attachments are present and bundles of fiber optic to take the excitation beam to the sample, which is placed remotely, and bring back the emission beam to the emission monochromator. Next is the detectors. There are two types of detectors, that is, signal and reference detector. The signal detector is based on photon counting, which is an R928P photomultiplier tube that directs the signal to a photon counting module. The reference detector's purpose is to monitor the xenon lamp for correction of wavelength and time-dependent output of the lamp. This detector is based on UV, which enhances silicon photodiode, which is placed just prior to the compartment of sample. We will now discuss the applications of photoluminescence. The first application is the determination of band gap. Band gap represents the energy difference among the conduction band, which is the top, and the valence band, which is the bottom in semiconductors exhibiting radiative transitions. The range of photoluminescence spectrum of a semiconductor is used for non-destructive analysis of band gap. Through this mode, it is possible to quantify the composition of the element of a semiconductor compound as well as its crucially significant material specification influencing the device efficacy such as solar cell. The second important application of photoluminescence is the identification of level of impurity as well as defect. Some localized defect levels are created when radiative transition occurs in semiconductors. Particular defects related to these levels can be recognized by the photoluminescence energy, whereas their concentration can be ascertained by the PL amount. The photoluminescence spectra of the sample at low temperatures often reveals peaks of the spectra linked with the impurities present inside the material of forest. Highly sensitive Fourier transform photoluminescence microspectroscopy have potential for recognizing very small concentrations of intended and unintended impurities, which strongly influence the quality of material as well as performance of the device. Another important application of the photoluminescence is the recombination phenomenon. Both the radiation and non-radiation based processes involve the mechanism known as recombination. Recombination means return to equilibrium. The emitted photoluminescence quantity of a material is straightaway linked with the relative quantity of radiative and non-radiative recombination rates. The quantity of photoluminescence and impurities are commonly linked with non-radiative rates, and it is dependent on the photoexcitation level plus temperature, which are directly associated to the dominant recombination process. Hence, qualitative PL analysis includes the monitoring of the change in material quality as a function of some conditions like growth as well as processing, which helps in understanding the fundamental physics of the recombination mechanism. Another application of interest is the surface structure in excited states. Some broadly utilized conventional techniques like XRD, IR, and Raman spectroscopy are very frequent, non-sensitive for catalysts, which are oxide supported with less concentrations of metal oxide. Photoluminescence, on the other hand, is too sensitive to surface effects or semiconductor-based particles absorb species. Therefore, it is utilized as a probe of electron hole surface processes. We next study the photoluminescence spectroscopy limitations. In spite of the fact that this technique is not qualitative in nature, it can be used to detect low concentration of optical centers. The major scientific PL limitation is that several optical centers might possess numerous excited states that are vacant at low temperatures. Another major limitation of PL is that the luminescent signal gets disappeared. For example, in the PL characterization centers of silicon, no sharp line PL from 969 milli-electron-volt centers were observed when they had captured self-interstitials. So students, let us now summarize what we have learned in this module. Firstly, in this module, the basic principle of photoluminescence was studied. Secondly, all the types of photoluminescence configurations were explained. Third, the basic instrumentation of photoluminescence experimental setup was explained. Then the applications of photoluminescence was studied. Finally, photoluminescence spectroscopy limitations was studied. Thank you students for your attention.